Okay, it's almost nice 9:30. I don't think many people are going to join because of the last minute notice. But I said it will be on Monday, but I forget to announce the time. So that's my mistake. We'll start with the meeting directly so that we can at least share the recording on time. So I will share the screen. I hope the screen is visible. Well, I will also join using my PC. Okay. So we are going to revise the whole chapter. Chapter number 4, linear differential equations. Linear differential equations. So we are going to focus only or majorly on linear differential equations with constant coefficients. We are going to focus on linear differential equation, majorly on linear differential equation with constant coefficients. So what do I mean by constant coefficients? So the general form, the general form of these differential equations of these differential equations is some Pn d power n y by dx power n plus Pn minus 1 d power n minus 1 y by dx power n minus 1 and so on till we get the last values as Pn dy by dx plus p naught y is equal to q of x. We are talking about general linear differential equations with constant coefficient. If my right hand side is 0, if q of x is equal to 0, then they are called homogeneous. They are called homogeneous. And if q of x is not equal to 0, in that case, they are called non-homogeneous. Non-homogeneous. Now, let me introduce you to one notation which is called differential operator. Differential operator. This notation will be used throughout the chapter or throughout this revision. Even in the question paper also, I may ask you question using this differential operator. So what that is denoted by? It is denoted by capital letter D, and this is defined as and is defined as it's defined as D is equal to D by dA. So it represents the first order derivative. So by dy, I mean dy by dx. By d square y, I mean d square y by dx square, and so on and so on. Similarly, 1 by d represents integration some dot dx. So it represents integration once. That is 1 by d of y. By this I mean integration of this y dx. by 1 upon d square y, I mean double integration, or instead of integration of y dx, the whole dx. So I'm taking twice integral. Integration, integration twice, and so on. And so on. Notice that, notice that I'm trying to keep, I'm trying to keep logical argument, logical argument that my d into 1 by d of certain function, say y, should be y. Since this d represents differentiation, this must represent an integration. This must represent an integration because integration of differentiation of same function is the same function. So to keep that part intact, I will be writing this equation or this notation. Now let's focus on the given equation first. So general equation. I'll be copying this equation. I'll copy this equation and we will start studying about this equation from now onwards. So this was our given equation. So the above equation in differential operator form, in differential operator form, in differential operator form can be written as, can be written as Pn, it's a constant. So as it is, notice that for d power n, for this quantity, I will use this laser. So for this quantity d power n by dx power n, we are actually using, from this notation, we can see we are using d power n for d power n by dy power n. Sorry, dx power n. D power n is equal to d power n by dx power n. So in adding y both side will give us the first term, this term. Okay. By that notation, I can rewrite this as d power n y. By similar argument, I can rewrite the next term as capital D power n minus 1 of y and so on till I get P1D of y plus P naught y is equal to Q of x. Q of x is a alone function of a x variable, so we are not harming it anyway. Now notice that we can take this y's common from left hand side, and by taking this y's common, we can rewrite the equation as Pn d power n plus Pn minus 1 d power n minus 1 y plus and so on till I get P1D plus P naught times y is equal to Q of x. So let's call this above equation as equation number 1 and let's call this as equation number 2. So these two equations are same equations but the different representation. Now we'll see how to solve equation 1 or equation 2. Notice that both the equations are same. So solving equation 1 or solving equation 2 doesn't mean anything different. So we are going to see an algorithm to solve these equations. So for that, the first thing is calculate CF, which is called complementary function, complementary function for 1. To calculate complementary function for 1. So for that, here are the steps that are required. So consider equation 2. So consider equation 2. That is equation in the operator form. This equation, consider this equation. Then in the next step, replace Q of x by 0 and and d by m. So in above equation, we will get Pn m power n plus Pn minus 1 m power n minus 1 and so on till we get P1m plus P naught is equal to 0. So I'm replacing this q of x as 0 and every d by m. Okay, I'm replacing every d by m. I'm replacing every d by m. So there is no d, so that's why there is no replacement. And this q of x as 0. So we are getting we are getting an an n degree polynomial n degree polynomial. So so it will have n roots. N roots. I am not claiming that they must be real, they must be distinct or anything. I'm just saying that there will be n roots. Okay. So say I'm calling them as M1, M2, and so on till Mn. So I will have these many roots. So I will have n roots. Note that I'll just write it as a note. We are not claiming, we are not claiming that they all they all should be distinct or real or anything else. Anything else. So they are just roots. We are not claiming anything or the behavior of those roots. So we will get n roots. Now, depending upon how my root looks, I'll rewrite the solution component for a root. Consider a root, let's say mi. Let's say mi. Then the solution component component corresponding to mi is, so there are three cases. First one, or we will majorly divide it into two cases. The first one, mi is repeated or appeared. Mi is appeared k times. Mi is appeared k times. So by that I mean there are k different equal roots. So they, for the expansion, I will have m minus mi power k, this term in the expansion of some f of m is equal to 0 for above equation. For above equation, this equation number 3 can be rewritten like this one. Okay, so by appearing k times, I mean the root mi is repeated k times. So in that case, then solution component is solution component solution component is yi is equal to ci1 e to the power mix plus ci2 x into e to the power mix and so on till we get the kth component or kth term as cik x to the power k minus 1 e to the power mix. Okay, so we'll get this k different components. So there are k different values or k different terms in the solution component for mi. Now, this is if mi is repeated k time. What if mi is complex? What if mi is complex? Which will imply there will be some mj which is equal to mi conjugate. There will be some mj which is mi conjugate. That is if mi is a plus ib, then mj should be a minus ib. Then in that case, then then solution component solution component for mi and mj combined. So we will combine the solution component for these two things is given by is given by mi yij is equal to ci, or before ci let's write down e to the power ax times ci cos ax cos bx plus c cj cj sin bx, where notice that this a is my real part, is my real part of that complex number, and b is imaginary part of my complex number. So this is, in this way I'll be getting my solution component. And finally, so uh, the complete root or complete CF, we are calling it point number 4. So point number 5, the complete complementary function is sum of all solution components. Sum of all solution components. So we'll see in the example how we can calculate the complementary function for a question. So before that, before that, we'll discuss the second major step of this one, which is called calculating calculating particular integral. Calculating particular integral. So for to calculate particular integral, to calculate, so I will say one, to calculate the particular integral, this pi stands for particular integral. So integral, to calculate particular integral, we consider the equation 2 as some f of d times y is equal to q of x. So notice that here f of d is defined as pn d power n plus pn minus 1 d power n minus 1 and so on till we get p1d plus p0. Okay, this polynomial is defined as f of d. Then the pi is given by is given by pi is equal to 1 upon f of d times q of x. So here we need to find meaning of this term of this term. So what is meaning of this 1 upon f of d, this term? So we need to find out, or we need to calculate what is 1 upon f of d represents. Okay, so there are 5 different rules on the basis of which we can take out the meaning of this term, and I will just list them down and we will start dive into examples where we will use all these meanings. Okay, so let's start. So suppose given equation is given equation is f of d times y is equal to q of x. So I will say SR1, SR number. Consider first as my right hand side. So this q of x is my e to the power ax. In that case, my particular integral will be x to the power k into 1 upon f of get the derivative of a times e to the power ax, where this k represents multiplicity, or how many times it is repeated as roots of this value a. So multiplicity of a in f of m is equal to 0. So notice that f of m is equal to 0 is our same auxiliary equation. This auxiliary equation, when we solve this, when we will get n roots, if a is a repeated root, if a is the value of a root, then we have to consider or we need to take the derivative to remove that as a root. And if if the and to compensate this derivation process, we need to add an extra x, or we need to multiply by an extra x. We'll see in one example when a is a root once, a is a root twice, and a is never a root. So in an example, we will see what to do when a is a root for multiple times. Okay. Now consider q of x as cos ax or sin a. In this case, I will just say it is trigonometric of x, t of x. In this case, in this case, it will be given by x to the power k into 1 upon g to the power k of minus a square of this trigonometric of ax. Notice that I have written f of d here and I am using d. So what is the relation? So I'm considering my particular integral, this 1 upon f of d of trigonometric of ax as a function of d square of trigonometric of ax. And again, this k represents again the multiplicity or how many times it is repeated as a root of ia in f of m is equal to 0. Notice that in this case, we are going for ia as a root, and for the first case we are going for a as a root. Okay, that's the difference. And we are replacing d square by minus a square. This d square as minus a square. Not in the previous case we were replacing d by a, and here we are replacing d square by minus a square. We will see some examples regarding this. Third one, when we have a polynomial, let's say an x power n. Since we are considering degree n, so for that we will consider some another number. So consider the okay, forget it, x n power n, an minus 1, x power n minus 1, and so on till we get a1x plus a0. In this case, we do have two different rules. One will calculate fd of inverse. Let's call this as polynomial in x. Of this polynomial in x, the rule number one, where we will use the fact that 1 plus 1 upon u can be written as 1 minus u plus u square plus u cube uh, minus u cube plus u power 4 and minus so on. And second thing, will assume will assume our particular integral as some capital an x power n and so on till we get a1x and finally a naught, and we will take the derivative, substitute the values in the equation, and we'll calculate the values of this an minus 1 and so on till a naught and a1. Then if my right hand side is e to the power ax into some another function phi of x, in this case, my particular integral can be written as this 1 upon f of d times e to the power ax times phi of x, can be written as, I will take this e to the power ax outside, and to compensate the difference, I'll write down this as f of d plus a. So I will shift my d to d plus a, and I will take this operation on phi of x again. So I don't need to take operation on e to the power ax. And finally, any any general q of x. In this case, I'll write down my solution as summation I going from 1 to n, 1 upon d minus mi or mj, writing mj might be look better, of q of x. So I'll write down this as this by a partial fraction. I will separate out all the terms and summation j equal to 1 to n aj divided by d minus mj of q of x, and the solution will be given as e to the power mjx into integral e to the power minus mjx into q of x dx. So we have explained how this formula come in the class, but again, the derivation is not important. We are going to see how to use the equation. So let's start with the examples. Let's start with the examples. So I'll be considering these 5 examples. I'll cut this and go to the last page, and we will start by the first example. So consider the example d cube minus 5d square plus 8d minus 4 is equal to e to the power 2x plus e to the power x plus 3 times e to the power minus x. Okay. So observe that since I am having an alternating signs, and notice that this is coefficient, some of these coefficients is 8, some of these coefficients is minus 9. Oh, sorry, some of these two is 9, some of these two is minus 9. I will total sum is 0. So one is a root. One is a root. So first thing we should write down the auxiliary equation. So the auxiliary equation, the auxiliary equation, from now onwards, I will be using AE for the short form of this auxiliary equation. So the auxiliary equation for above differential equation is m cube. So replace d by m minus 5m square plus 8m minus 4 is equal to 0. We have noted down that m minus 1 is a factor. So whatever that bracket is, we need to calculate. So I will be using synthetic division. So I will write down the coefficient minus 5 plus 8 and then minus 4, 1 as it is, this 1. So 1 is the root, minus 4. So my 1 into minus 4 is minus 4 plus 4. 1 into plus 4 is plus 4. So I am getting remainder as 0. And my right hand side as 1 minus 4, sorry, not 1, m square minus 4m plus 4 is equal to 0. Notice that this also can be written down as m minus 1 into m minus 2 whole square is equal to 0. So therefore, m is equal to 1, m is equal to 2, and m is equal to 2 are roots. So these are roots. Now CF is given by CF is equal to, write down all the solution components for these roots. So for m is equal to 1, we have C1 e to the power m1x, right? So we will have C1 e to the power x. Notice that 2 is a repeated root and it is repeated twice, two times repeated, two times repeated root. So for 2 times repeated root from our given equation, or if a root is repeated k times, here 2 times, we have to write down 2 components. So till this point. So Ci1 into Mix plus Ci2 into x into Mix. So for this k equal to 2, m equal to 2, you can write down as C2 into e to the power 2x plus C3 x into e to the power 2x. So this is my complementary function. Again, one more thing. Uh, The final step is complete solution to above d to above differential equation is y is equal to cf plus pi. This will be our final step for every question. This will be the final step. And one more thing, the zero, SR number 0, if my q of x is 0, my particular integral is always 0. Okay. So if there is no right hand side is 0, particular integral I will consider as 0. So nothing to do with that. Okay. So I have calculated my complementary function. Now to calculate, now to calculate particular integral, we know particular integral is given by 1 upon f of d times q of x. In this case, 1 upon f of d was d cube minus 5d square, then plus 8d minus 4, and q of x was given by this big quantity or big expression or big things. So I'll change the style to white. Right. Notice that this term sitting here is some combination of differentiation and integration operations. Okay. So this is a combination of integration and differentiation. So, so, so that's why we can distribute this thing to all these things separately or these terms separately. So I will just copy this part and write down the same thing 3 times. Write down same thing 3 times so that I can distribute them well. So I will take this a little up and I will again paste it. So I have written the thing 3 times. I'm trying to distribute this operation to e to the power 2x, 2 times e to the power x, and 3 times e to the power minus x. Okay. So remember the rule which we have studied before. If my right hand side is e to the power ax, in that case, I will have x to the power k 1 upon f of kth derivative at a times e to the power ax, where k represents the multiplicity of this value a, the value a which is sitting here in f of m is equal to 0. So we know 1 is a root, 2 is a root, and 2 is also root. So 2 is repeated twice root, and 1 is repeated once root. Okay. So this two is repeated twice. So we need to take the second order derivative of this quantity, and to compensate the second order derivative, we need to add x square. So what is the second order derivative? I will have derivative of x d cube at second derivative of d cube at 6d and minus 10 of e to the power 2x. Then since 1 is a root, I need to take the first order derivative, and I will take this 2 outside. It's a constant. So 1 upon this 3d square minus 10d plus 8 of e to the power x. And finally, since minus 1 is never a root, we can rewrite the same thing as it is. So d cube minus 5d square plus 8d minus 4 is into e to the power minus x. Now we need to evaluate everything by by replacing d by a. So we need to replace every d by a. In this case, d should be replaced by 2. In this case, d should be replaced by 1. And in this case, all these 3 d's should be replaced by minus 1. So by replacing all those quantities, we'll have x cube 1 upon this 6d, that is 12 minus 10 as 2 e to the power 2x plus 2 times. I need to replace d by 1. So this will give me 11 minus 10, that is 1 by 1. So I will not write that 1 by 1 as it is 1 e to the power x plus I will replace d by minus 1 to get this as minus 9 plus minus 9 minus 4 as minus 13, and this will have again minus sign. So minus 5 minus 13 minus 5 as 1 upon 18 e to the power minus 6. So I'm just and there is 3 sitting here, so it will be minus 1 by 6. So x square e to the power 2x by 2 plus 2 times e to the power x minus 1 by 6 e to the power minus x. So this is my particular integral. Again, this is not the end, not the end. We need to write complete solution. Complete solution adds y is equal to cf plus pi. So in this case, I will just calculate my particular integral and we'll paste it here. We'll paste it here and I will again copy the cf complementary function. I will copy that function and we'll paste it over here. So this is my complete solution. Y is equal to C1 e to the power x, C2 e to the power 2x plus T3 x into e to the power 2x plus x square e to the power 2x by 2, 2 into e to the power x minus 1 upon x, 1 upon 6 e to the power minus x. So this is my complete solution. We'll solve another problem of this type or on the similar line, but by different uh, by different substitution or by different rule of particular integrals. So consider this example. Notice that by replacing d by minus 1, I can get the value 0. So here my auxiliary equation is m cube plus m square plus m plus 1 is equal to 0. I can note that m minus 1 is a root. So I need to find out this bracket. So to find out that bracket, I'll rewrite all the coefficients and minus 1 as a root. So it will be minus 1, 0. Then 0. I will get 1 and minus 1. Again 0. So I will get m square plus m is equal to 0. So therefore, I will have m plus 1, m plus iota, and m minus iota is equal to 0. So iota and plus iota and minus iota will be my two roots and m is equal to minus 1 as my third root. So therefore, the roots are the roots are m is equal to or m1 is equal to minus 1, m2 is equal to iota, and m3 the conjugate of the same thing as minus iota. So I will write down 0 plus iota, 0 minus iota. Why? Because my complementary function is given by e to the power c1 e to the power minus x for m1, and for m2 and m3 combined will have e to the power 0x times c1 cos x plus c2 sin x, because real part is 0 and imaginary part is 1. So this can be rewritten as c1 e to the power minus x. I will write down c3 here. So c2 sin x plus c3 cos x. So this is my complementary function. Now to calculate the particular integral, we know the particular integral is given by 1 upon f of d times q of x. 1 upon f of d times q of x. In this case, f of d was d cube plus d square plus d plus 1. So this was f of d. And q of x was sine 2x cos 3x. Sine 2x plus cos 3x. Again, I will separate out the terms or distribute the operator. So this is d cube plus d square plus d plus 1 of sine 2x plus, again, I will write down the same operator, d cube plus d square plus d plus 1 of cos 3x. Notice that the roots were minus 1 iota, and minus iota. So 2 iota and 3 iota were never a root. So we don't need to take the derivative. We can directly go for the calculation. So remember, we need to substitute minus a square for d square. Okay, remember this part, that we need to substitute for d square, not d. Okay, so Wherever I can see d square, so here there is a part of d square which is given by d into d square. So here minus of a square will be minus 4 plus again minus 4 plus d plus 1 of sine 2x. For the next term, again we will have d into minus 9 because in this case value of a is 3 minus 9 plus d plus 1 of cos 3x. We can simplify this term as uh, minus of minus of 3d plus 1. Notice that 3d plus 3, right? 3d, this will be minus 3 and this will be minus 3d and minus 3. So again we can take that also common of sine 2x, and here I will have minus, again I'll go for minus 8d plus 8 of cos 3x. So I can take these negatives outside. So minus 1 by 3 times 1 upon d plus 1 of sine 2x and minus 1 by 8 taken outside, I will have d plus 1 of cos 3x. Notice that we can replace only for d square. We can replace only for d square and not d in this case. In this case. So only we cannot replace for anything for d. So we need to take d square in the denominator. So I will consider this like an algebraic operation and I will try to rationalize the thing. So for rationalization, I will multiply and divide by d minus 1 to both the expression of sine 2x and minus 1 by 8. Again, d minus 1, notice that it will be d square minus 1 of cos 3x. So this will be d minus 1 divided by d square minus 1. So this will be 1 by 3. Here, we need to replace this d square by minus 2 for this case, minus 4 for this case. So it will be minus 5. D of sine x, sine 2x, differentiation of sine 2x is 2 cos 2x minus, as, as it is, minus 1 by 8. Same thing here. We will have minus 10 sitting in the denominator, differential of cos 3x as minus 3 sine 3x and minus the same thing. So this is we are operating d of sine 2x to write down this 2 cos 2x and minus 1 times cosine 2x as minus sine 2x. Okay. So I will cancel out these negatives. I will have 1 by 15 2 cos 2x minus sine 2x, and notice that there are three negatives, so I will write down minus 1 by 8 times or minus 1 by 80 times 3 sine 3x plus cos 3x. And notice that this is not yet my complete solution, this is just my particular integral. So therefore the complete solution is y is equal to CF plus PI. I will leave this part for you guys to write it down. We'll dive into the next example directly. So consider this example. Consider this example. So we are having d power 4 plus 2d square 2d cube minus 3d square of y. Okay, this y should not be here. Y should be outside. Of y is equal to x square plus 3e to the power 2x plus 4 sine x. So I will leave calculating particular integral for this later part for you guys for an exercise. I'll just calculate for this x square during this question. So here auxiliary equation is given by auxiliary equation is given by m power 4 plus 2m m cube minus minus 3m square is equal to 0. We can take m square common. So we will have m square plus 2m minus 3 is equal to 0. And therefore, we can rewrite this as m square m minus 3 m plus 3 into m minus 1 is equal to 0 by splitting the middle term. And therefore, therefore, the roots are m is equal to 0, m is equal to 0. So they are repeated roots. And then m is equal to 3 and m is equal to minus 1. M is equal to minus 3 and m is equal to plus 1. These are the roots. So therefore, the complementary function, the CF, is given by the CF is given by CF is equal to C1 plus C2 x. Notice that I am not writing that e to the power 0x because e to the power 0x is 1. Okay. Then C2 e to the power minus 3x, not C2, C3, and C4 e to the power x. So we have 4 components for our 4 roots. All the CF is calculated. Complete CF is calculated. Now the particular the particular integral is y is equal to, or pi is equal to, instead of y we are using for complete solution. So pi is equal to 1 upon f of d times q of x, which in this case is d square m uh, plus 2d minus 3 of x square and whatever the rest of the terms for which you need to calculate. So I'll just consider pi 1 as 1 upon d square times d square plus 2d minus 3 of x square. I'll rewrite this as 1 upon d square into d plus 3 into d minus 1 of x square. So for starters, I will focus on this part. So 1 upon d minus 1 of x square. Remember the rule? 1 upon 1 plus or 1 minus u is written as 1 plus u square plus u cube and so on. Okay. So I'll be using this rule. So this can be written as 1 upon, I will take this negative outside, so minus 1 upon d square in bracket 3 plus d times 1 upon 1 minus d of x square. Okay. Now minus 1 upon d square 3 plus d is as it is. Is as it is. Well, I will be sharing my notes, but at least join the meetings. Well, I am getting the messages. I thought messages will be related to meeting, but I'm getting messages related to the ISCs and notes. Well, I will be sharing the notes. Don't worry. We'll have 1 plus d square. Note that I won't be writing plus d cube and all those things, even though they are a part of the expansion. But the third derivative of x cube, x square is 0. Whole derivative will be 0. Fifth derivative will be 0. So therefore, I'll be calculating till I get the nth derivative where I'm having nth degree polynomial on my right hand side. Here n is 2. So I'll be writing till like d square of x square. So this quantity is minus 1 upon d square d plus 3 times 1 into x square is x square, d into x square is 2x, and d square into x square is 2. Again, I'll take minus 1 by 3 common and I will write down 1 upon d square times 1 upon 1 minus 1 plus d by 3 of x square plus 2x plus 2. Again, note that I am having a degree 2 polynomial on my right hand side. I will be writing 3 terms. So I will have minus 1 by 3 into 1 by d square times 1 plus d by 3 plus d square by 9. This whole square, notice that there is complete of u square there. Okay, and since there is a plus sign, I need to start by alternating signs. So plus minus, but I will not be writing d cube term because I'm having quadratic term on my right hand side. So this can be written as 1 by 3 into d square into 1 times this expression is x square plus 2x plus 2 minus 1 by 3 differentiation of this expression is 2x plus 2 and minus plus 1 by 9 of 2 times of 2 twice differentiation is 2. So this can be written as minus 1 by 3 minus 2 by 2 by 3 will be plus 4 by 3 x 2, then minus 2 by 3 again 4 by 6 4 by 3 and plus 2 by 9. So 4 by 3 plus 1 by 9 2 by 9 will be 10 by 9, not 10. It should be multiplied by 3 so it is 14 by 9. So again note that we haven't calculated our we haven't completed all the operator terms yet. We need to still go for this d square. So note that 1 upon d square means differentiation taken twice. 1 upon d square means integrated twice. So integration twice of this quantity will be x power 4 divided by 12. Integration twice of this quantity will be 2 by 9 of x cube, and integration twice of this quantity will be 6, not 6, 7 by 9 of x square. So this is my complete particular integral. So write y is equal to cf plus pi as your complete solution. Complete solution. Okay. So that complete solution should be written as y is equal to cf plus pi. Now consider this example. So I will just cut this part. Okay, I guess I haven't included anything for the generic version, generic solution. This is for rule number 4. Again, the auxiliary equation will be m square minus 4 is equal to 0, which will give me m is equal to 2 or m is equal to minus 2. So note that roots are repeated. So therefore, CF is given by C1 e to the power 2x plus C2 e to the power minus 2x. Now, to calculate my particular integral, I need to go for pi as 1 upon d square minus 4 of x into sine hyperbolic of x. But sine hyperbolic of x can be written as e to the power x minus e to the power minus x divided by 2. So which again can be expanded as 1 upon d square minus 4 x into e to the power x by 2 minus 1 upon d square minus 4 into x into e to the power minus x by 2. So from the formula table that we have done, consider this one e to the power ax times phi x can be written as e to the power ax taken outside, and we will shift d as d plus a. We'll shift d as d plus a. So in this case, I'll take this e to the power x by 2 outside and shift my d as d plus 1 whole square minus 4 of x. And in the second case, again, I will take e to the power minus x outside. So I will shift my d as d minus 1 whole square minus 4 of x. This can be evaluated as e to the power x by 2, 1 upon d square plus 2d. It will be plus 1. So this will be minus 3 of x minus e to the power minus x. This will be e to the power d square minus 2d and minus 3 of x. Okay. Now, to calculate the solution, and consider this as pi1 and this quantity as pi2. pi1, pi1, okay, I will just consider this part and this part for my easiness. So pi1 must be ax plus b because my right hand side is a linear polynomial. So consider this as yp, so which will give me yp dash as a and yp double dash as 0. So note that this is the solution of the equation y double dash plus 2y dash minus 3y is equal to 0. So substituting these quantities in the equation, we'll get minus 3 ax minus 3b, then plus 2a. Everything should add up to 1 times x. So by comparing coefficients, we can write down a as minus 1 by 3, and by since a is minus 1 by 3, since a is minus 1 by 3, we will have minus 3b minus 2, 2 by 3 is equal to 0, which will give me the value of b as minus 2 by 9. Okay, so my pi1 is minus 1 by 3x minus 2 by 9 minus 2 by 9. Similarly, for for pi2, we have pi2 should be cx plus d, which is, let's say, again yp or yp dash. So therefore, we have yp dash dash as c and yp dash double dash as 0. Again, substituting in the equation, substituting in the required equation. Where is that? This one. So minus 3 again. So we are having minus 3cx minus 3d and then uh, minus 2d. So minus 2c. Note that this d and this d is different. I should use different notation. So let's see. Let's use e, and this should be x again. So this will imply value of c as again 1 minus 1 by 3, and this will again imply 3e minus 3e plus 2 by 3 should be 0, which will give me value of e as 2 by 9. So therefore, my particular integral 2 is minus 1 by 3 x plus 2 by 9. So therefore, my complete particular integral is e to the power x by 2 times minus 1 by 3x minus 2 by 9 and minus e to the power minus x by 2. There was minus sign in between, right? Yeah, minus sign. So minus e to the power minus x by 2 minus 1 by 3x plus 2 by 9. We can just simplify the terms like e to the power minus x by 6 minus this 2 and 2 will be cancelled. So e to the power minus x x times by 9, and everything here is negative. So e to the power x by 6 and again minus again x times e to the power x by 9. Okay, we can also club the terms for writing down equation in terms of sine hyperbolic and cos hyperbolic. But again, it's up to you. Do you want to proceed for that or not? Okay. So I will leave this as my particular integral, and again write complete solution as y is equal to CF plus PI. Y is equal to CF plus PI. Okay. So for the last example, I guess I said I'll be taking an example uh, from the previous slide or from the notes, which was given as a homework. So I'll just copy that part. So where was that? So for rule number five, where was that? Where is that last expression? Okay, this one. This one given as homework for near many classes. So I will just not cut. I should not have cut that. I need to copy that and paste it here. So consider this example. Again, calculating particular integral for x, I will leave this as an exercise. You can calculate it or you can complete it. So I'll start by calculating the auxiliary equation. So auxiliary equation in this case is m square plus 1 is equal to 0, which will give me m minus iota and m plus iota is equal to 0 as my factorization, and therefore m is equal to iota and m is equal to minus iota are roots. Since I have complex root, my complementary function is given by C1 cos x plus C2 sin x. Now, now particular integral is 1 upon f of d pi is 1 upon f of d times q of x. In this case, it is 1 upon, I can rewrite this as d minus iota and d plus iota because these two are the roots from above. And I will just consider only for cortex. Okay. So I will say pi2 I'm calculating. Pi is complete one, and pi1 here is 1 upon f of d times x, which can be calculated easily. And notice that by observation, I can directly write down that as a x, but I will recommend to go through the process to calculate this value. Okay. So this can be again rewritten as 1 upon 2i times 1 upon d minus I minus 1 upon d plus I times cortex. Well, to achieve this part, we need to go through partial fraction by saying this is a into 1 minus d plus I times b upon 1 plus d plus I is equal to 1 upon d plus 1 d square plus 1, and then solve for this a and you'll get this quantity. I'm directly writing down because my terms are simple and I can easily guess the terms. So I'll consider only 1 upon d minus I of cortex. So by d minus I of cortex, I will have e to the power ix into integral e to the power minus ix into cortex dx, which can be written as e to the power ix. E to the power minus ix is cos x minus I sin x minus I sin x times this is cos x divided by sin x dx. So this can be evaluated as e to the power ix integral of cos x into cos x as cos square x divided by sin x minus I times cos x dx, which can be also written as e to the power ix into 1 minus sin square x divided by sin x minus I cos x. So integral of this big quantity, so bracket should be here and bracket should be here. Okay, I haven't missed any bracket yet. Dx e to the power I into 1 minus or 1 upon sin x is integral of cosec x minus this one is integral of sin x and this one is I times cos x dx. Note that integral of cosec x is log of cosec x minus cot x. Integral of sin x is plus minus of cos x, so it will be plus cos x minus minus will become plus, and finally this term will become minus I sin x because integral of cos x is plus sin x and there is a minus sign sitting here. So this one is 1 upon d minus I of cot x. Similarly, we can rewrite d plus I of cot x by replacing every I by minus I. So here will be e to the power minus ix log of again cosec x minus cot x plus cos x. There is no I, but here is I, so I need to revert the sign. And therefore, 1 upon 2I times 1 upon d minus I plus, minus 1 upon d plus I of cot x can be written as, so first term is this big term. So I'll write down it as cos of log of cosec x minus cot x plus cos x, and from the first bracket I will take this e to the power ix, then minus this one is minus, and from second bracket I will have e to the power minus ix, and note that it is divided by 2I. It is divided by 2I, and then minus this sin x I sin x, and again from the first part I have e to the power ix, and notice that there is a plus sign is reversed, so I need to add an extra negative, but there is again one negative, so it will become plus e to the power ix divided by 2I. So I can cancel out this I and rewrite this as, notice that e to the power theta I theta minus e to the power minus theta I theta by 2I is sin theta, and e to the power I theta plus e to the power minus I theta, here is minus, so e to the power minus I theta divided by 2 is cos x. So we can rewrite this expression as log of cosec x minus cot x plus cos x into sin x, and this one minus sin x into cos x, out of which these two will get cancelled. So therefore, my particular integral 2 is log of cosec x minus cot x. Okay, so this is my particular integral 2. So my particular integral total will be pi1 plus pi2. That will be x plus log of cosec x minus cot x, x plus log of cosec x minus cot x, and my complete solution will be cf plus pi. So write down the complete solution as cf plus pi. Okay. So we'll move on to the last equation or last expression of this series. Last question. So I will cut this part and again I will paste it over here. And notice the difference between the previous questions and this question. Here we are having this x square or 2x as the coefficient. These are not constant coefficients, so they are called Cauchy-Euler linear differential equations. Okay. For Cauchy-Euler, I mean the every term will have the form of x power some pn into x power n dn power y by dx power n. So every term will be of this form. So notice that we are having x square and second order derivative. We are having x, so first order derivative. We are not having x, so none derivative. Okay, this will be our Cauchy-Euler linear differential equation. Now, now here this d power n y is substituted as d script d minus 1, script d minus 2, and so on till I get the nth term as script d minus n minus 1. So this is the substitution that we will be using, and to get this from here, we need to put x as e to the power z or ln x as z. So this is the substitution that we are needed. This is the substitution that we are needed to convert our linear differential equation. Okay, there should be x power n sitting here. So x power n into d power n y is can be written as d into d minus 1 into d minus 2 into and so on till the nth term, that is d minus n minus 1. So for this expression, given equation is given equation is x square y double dash plus 2x y dash minus 2x y dash plus 2y is equal to 4x cubed. So by that change, we will have d into d minus 1 of y minus 2d of y plus 2y is equal to 4. Notice that x is also substituted as e to the power z, e to the power z. So this will be e to the power 3z. So therefore, I will have d square, this minus d minus 2d, that is minus 3d, and then plus 2 of y is equal to 4 times e to the power 3z. So again, we reduce this to our linear differential equation of constant coefficients. So here auxiliary equation is m square minus 3m plus 2 is equal to 0, whose roots are m minus 2 and m minus 1 is equal to 0. So roots are m is equal to 1 and m is equal to 2 are the roots. So therefore, my CF is given by C1 e to the power M1, in this case 1Z. Notice that we are getting the solution in terms of Z, but we don't want solution in terms of Z. We want the solution in terms of X. But we know e to the power Z is X, and e to the power 2Z, which is e to the power Z whole square, is X square. Okay, so this is my complementary function. Now particular integral Now, particular integral is 1 upon f of d times this q of z. In my case, 1 upon f of d was d square minus, okay, I'm using the strict d notation. So I'm having d square minus 3d plus 2 of 4 times e to the power 4z. Notice that 4 was never a root, or 3z. 3 was never a root. So therefore, we'll have 4 times 9 minus 9 plus 2 of e to the power 3z as my particular integral, which will be 4 by 2 e to the power 3z. Again, rewriting this z into x, we will have 2x cube as my particular integral. So therefore, the complete solution, the complete solution is given by y is equal to cf plus pi. In my case, it was c1x plus c2x square, and my particular integral was turned out to be 2 into x cube. So this is my complete solution. Notice that my final solution must be in terms of x because my question was in terms of x. So even if I'm going through the substitution at for z, my final solution should not be the solution of z. Okay, so we will stop here. If you have any doubt, we can you can message me. I will share these slides and also the regular lecture slides with you in 5 minutes. I need to just make some y changes here, there, here and there. I guess in some problem I missed that extra y in some problems only. So I will just change that and I'll share the slides, all the notes. So note that you will be having your well this is instruction for only for CSE unaided and IT unaided and Robo Auto R3 batch. You will be having your ISC. You will be having your ISC on in the next week, starting from Monday during your tutorial session. Okay, so make sure to practice well. I'll share both the slides and this video in 5 minutes. So thank you. We can stop here. I hope there were some participants. I can see only one participant right now. So thank you.